transformer. Now the design problem is what is given is the rating. In rating, it will be given the kVA rating, the voltage rating, primary and secondary voltage, the frequency, type, port type or shell type, then the type of cooling. Here it is single phase. So if it is 3-phase, the connection also, the vector connection, that will also be given. And what is specified minimal, this is, that is a percentage impedance. Temperature rise, tapping positions. If special applications, some other quantities might also be specified. Now from here, we have to decide the dimension. So dimension information has to be derived from these ratings. Now, I have just explained just a basic principle, that is in single phase core type we are discussing. So we know the shape of the core. For single phase, this is a rectangular core we will have with 2 limbs, and the empty portion in the middle, that is the window. Now the window dimension, that window accommodates the winding. So what is the volume of the winding, that will decide how large the window will be, because we won't allow any extra space, because that will make extra material cost. So AC, if AC is the area of the conductor, then area of the primary conductor plus area of the secondary conductor. Now area is cross section of the primary conductor into primary number of turns, cross section of the secondary conductor into secondary number of turns. If it is AP into TP plus AS into TS. Now AP is the area of the primary conductor, that will depend on the primary current, because current density, what we can allow, that depends on the type of device and the material we are using. Normally for power distribution transformer, copper is used. So it is a static equipment. So for copper, we allow 3 amp per millimeter square. For rotating machine, when you design, you will see that we can go for higher current density. So the area, primary area, will be primary current divided by the current density, which is constant for a particular material. Then the secondary area is secondary current divided by the current density. Now if in this equation, that is AC is equal to APTP plus ASTS, if we replace by IP by delta, then it becomes IPTP plus ISTS by delta, where IPTP is the primary current into primary number of turns, secondary current into secondary number of turns. So it is primary AT, secondary AT, they are equal, we know. So it is twice AT by delta. So where AT is the magnetizing MMF. Now if we define KW as a window space factor, but it is the ratio of total conductor area by the total window area. So AC by AW. So your AC, or the window area, which is that it is a window height and window width, that is the multiplication of height and width, that is KW into KW, is twice AT by delta. So AT, the ampere turn, will be delta KW AW by 2. This is for single phase, what I am talking about. So Q, the kVA rating, is Vp IP into 10 to the power minus 3, because this is kVA. So if we neglect the drops, which is very small for transformer, this is EP, IP into 10 to the power minus 3. So EP can be defined as ET into TP, where ET is the voltage per turn into number of turn into IP. So again, TP into IP is 80. So ET into 80 into 10 to the power minus 3. Now if we consider the sinusoidal flux distribution, so phi is equal to phi m cos omega t. So EP, induced EMF, will be 1 by root 2 omega TP into, this is RMS value, phi m, that 4.44 F TP into phi m. ET, that is the voltage per turns, will be induced voltage divided by the number of turns. So this is 4.44 F into phi m. So in the equation of the Q, we have ET, AT into 10 to the power minus 3. So if we put the values, ET will be 4.44 F into phi m into AT. We have seen that del kW AW by 2 into 10 to the power minus 3. So this can be written as 2.22 F phi m delta kW AW in 10 to the power minus 3. Then phi m is the flux density into iron area into delta into kW AW into 10 to the power minus 3. Here you can see that the kVA is being related to the dimension. AI, the area of the core, cross-section area of the core, and AW is the window area. So now this design as if varies with, if we consider this equation, varies with phi m by phi m and AT. This is AT, the electrical loading, and phi m is the magnetic loading. So the ratio phi t by AT is constant for a given type, service, and method of construction, because as we change this ratio, the characteristics and performance will change. So if we take that ratio is equal to R, then we put in this equation, in place of AT, we put phi m by R. So this equation becomes 4.44 phi m square F by R in 10 to the power minus 3. Then phi m can be written like this. Now in this expression, this F is for constant frequency, it is constant. R is the ratio which we defined as, it will depend on the type of construction, then the service, whether power or distribution. So it is constant for a particular type. So this value is a constant. So if we put in the equation of ET, it was 4.44 F phi m. So we have 4.44 F root over of this into root Q. Then this total thing is a constant. So constant into root Q. So this is our starting equation. This is our starting equation for transformer design. So Q is our kVA rating. So if we have a Q kVA transformer, so putting that Q value, K, as I have told that it will depend on the type. So there are different ranges. So you can select a value of K and start, because design is an iterative process. So ultimately you arrive, after iteration, you arrive at the required design. So you start with a value. So we particularly first calculate ET, or the voltage per turn. Now the V, I have, if you remember, I have defined the voltage as A kV by B kV. Now actually we start with the low voltage. I have considered a step down. So this B is the low voltage, because when we first we start from the low voltage side, because it is on the inner side. So this is ET, low voltage number of turns is B into 10 to the power 3 by ET. Now obviously number of turns should be an integer, and as it is a single phase transformer, we have an core type, so we have to arrange half of the turn on one limb and half on the other limb. So it should be an even integer. So whatever value comes here, it should be rounded off to an even integer. That is, say if it comes to be some 3.3 or something. So we have to go for 4. So even if it is a 3, we should go for 4, or we can go for 2 also, because it is a design process. So whether you will go for the higher or lower value, that depends on the designer and experience of the designer. So say then we opt for the nearest even integer. When you opt for the nearest even integer, now your voltage is fixed. So what gets changed? That is ET, what we have started calculated from this empirical equation. So ET modified will be your low voltage divided by the turn, what we have put here. So this ET modified is equal to this 4.44 phi m into F. Now F is known, ET modified known. So from this equation, what we calculate is phi m. So phi m is this, it is given by Weber. So this is equal to Bm into Ai. Now Bm is a flux density, as we will use CRGOS. So flux density operating will start assuming it is 1.75 Weber per meter square. So assuming flux density Bm, we can calculate Ai from this equation. Now one thing, what happens for a particular rating we are given, we can have different n number of designs, which will give more or less same performance and the same rating, the same output. Now what happens if we start with a value of k, then you will get certain design. Now you change the value of k, say we increase the value of k, then what will happen? If you increase the value of k, value of ET will increase. If ET increases, that means your phi m increases. Now the material is same, so Bm is constant. So if phi m increases, that means Ai will increase. That means your iron area will increase. So that will increase your core material. And as ET has increased, so what has the that number of turns, that will decrease because your voltage is constant. So your copper weight will decrease. So if ET increases, your iron weight will increase, copper weight will decrease. So your iron cost will increase and copper cost will decrease. But it can be shown that the minimal cost, that is the summation of these two, this is a rough figure, just hand-drawn figure, which will be summation of these two. This will change like this. The minimum occurs at this point where copper cost is equal to the iron cost. So this is the minimum cost point. So for different values of k, you will get different designs. This curve you will get provided that you are designing for same flux density and same current density. And the performance will be more or less similar. So you can have a number of n number of designs, dimensional designs with the same KV output. So now once you have Ai, that is called the net iron area. Now what is gross iron area? Actually laminations have are insulated on both sides. So these insulations are very thin, but some area it will take. So the stacking factor is defined as net iron area by gross iron area. And for CRGOS, taking 0.35 millimeter thick lamination, it is 0.97. So our gross iron area will be Ai by 0.97. Now actually what is the stacking factor? That depends on the thickness of the lamination, and only not on the thickness, the material also, the finish, that is smoother the laminations, better will be the stacking factor. If it is rough, then for the same thickness, the stacking factor will be smaller. HRS previously used has higher stacking factor because we cannot go for thin lamination, it is thicker. So this is a table given, that is we will go, we know that the say code will be stepped. Now how many steps you should use? Now that depends on the iron area. Now very small transformer, these values are Ag into 10 to the power 3. That is whatever be the value, multiplied it by 10 to the power 3, because that is in meter square. So this will be very small. So into 10 to the power 3, that is this quantity. So if it less than 3, then a single step, that means a rectangular or square section. Similarly, as we go on, the number of steps increases. For higher number of steps, we have to go for the duct, because the it is becoming larger and the gap between the winding and the core is also less, so less ventilation. So for ventilating, duct has to be provided. Now next is the core circle diameter. Core circle diameter, if D, then we define a ratio R is equal to Ag by pi by 4 D square. That is a Ag actual stepped area divided by the circular area. Now that ratio also depend on the number of steps. Now, so once you decide Ag, you know how many number of steps you have to use, and once you know the number of steps, you know what is the ratio R. So select R from here, put R here. So Ag, you know, from this equation we determine D, or the core circle diameter. Now then we have to calculate the dimension of the steps. Now when we this one I have shown is a 4-step core. When we say the 4-step, that means in half cycle we have 4 steps. Now how to calculate the dimensions? Now all these corner points, this figure is not perfect because this point should be here. So all these corner points should lie on the circle. So what happens that for the first step, this is a core circle diameter D. So for the first step, this was A1. Now A1 is taken equal to D. Now D has to be rounded off to multiple of 5 millimeter. Rounded off to multiple of 5 millimeter. So then A1 is taken as D minus 5. Now then we should have this B1 and in this case B4. If we have n step code, then this is AN. This should be, these two dimensions should be equal. Then this structure will approximate a circle. So for this, if we want that, then this angle, if this angle is theta, this angle is also theta. Now this angle theta can be determined because we know this is D by 2 because this is the radius of the circle and this is A1 by 2. So we can determine this angle theta once and also this total is B1. So B1 by 2 will be this D by 2 sine of theta. Now we also make this angle theta so that this and these are equal, and the remaining angle, that is this 90 minus 2 theta, is divided equally. Now if we have 4 steps, then we have 3 sectors in between. So 90 minus 2 theta is divided by n minus 1. So we determine this is A1 and B1, then this is theta. Then step 2 for n step 4, this is phi is equal to 90 minus 2 theta by n minus 1. For 4 step 4, phi is equal to 90 minus 2 theta by 4 minus 1. Now A2 will be for A2 we consider this triangle. For A2 will be this into 2. So this will be d by 2 cos of phi plus theta will give this into 2. So your A2 will be 2 into d by 2 cos theta plus phi. Similarly, b by 2 will be this minus b1 by 2. So this will be d by 2 sine of phi plus theta, d by 2 sine of phi plus theta minus b1 by 2. Now the thing is laminated in this way. So number of lamination to assemble to get this thickness B, B1, etc. should be multiple of number of lamination number of should be a integer. So lamination thickness we have considered is 0.35. So all B's, these B1, B2, B3, whatever we get, that should be made multiple of 0.35 millimeter. For step 3, again similarly, A3 will be 2 into d by 2 cos of theta plus twice phi. D by 2 cos of theta plus twice phi will get this. So minus, sorry, into 2 will be A3, and for B3 will be d by 2 cos of theta plus twice phi will get this side. So minus B2 minus B1 by 2. Again, that should be made multiple of 0.35. So similarly, we can get for the step 4. Similarly, it will go on as the number of steps increases. So after we determine all the values, now from here you can see that the values gradually decreases. That A1 greater than A2, greater than A3, greater than A4. Similarly, here also B1 is greater than B2, greater than B3, B3 greater than B4. So if that way it comes, you can understand that it is calculation is correct. Total gross iron area, actual gross iron area will be A1 B1 multiple of this, that is A1 into B1 plus A2 into B2 plus A3 into B3 plus A4 into B4 into 2 on both sides. So that is the total gross iron area actual. So AI modified will be, we have started with a value of AI, but now AI modified will be that stacking factor into the actual gross iron area. So our actual VM or the actual flux density will be the flux which we have calculated divided by AI modified, and it will be something different from 1.75 what we have started with. So it should we should allow it to be correct if it lies within 1.7 Weber per meter square to 1.8 Weber per meter square. So now we have decided the core cross section. Once we decided core cross section, next we will go for the winding. We start with the low voltage winding. Now here, this equation we have derived, Q is equal to this. Now in this equation, now we have this, we know BM actual, we know AI modified. Now we start assuming a value of KW. If we take a value of KW, then AW we can determine from here. Now this equation I have made some mistakes. That is. Anyway, I will check and correct mean the correct one. Some mistake. Something is missing. Anyway, we start with that KW value. We start with the empirical relationship, that is 10 to 12 divided by 30 plus high voltage in kV. Say your high voltage is 11 kV, then it will be 11. So 10 divided by 30 plus 11, then it will be a small fraction. So you start with the value of KW. This is a range. You can assume any value in between. So AW will be KW divided by this. So we know a value of AW. Then AW is window height into window width. Window height into width ratio, we should be in the range of 2.5 to 3.5. So assuming a ratio in this range, we will get values of HW and WW. Window height and width. Now next is the low voltage winding. So low voltage winding, this is the low voltage current, will be the kVA rating divided by low voltage voltage. Now what will be the type of winding depend on the rating, current rating and voltage rating. If less than 11 kV, we go for spiral or helical winding. For higher current, it is better to go for helical winding. Up to 100 ampere, we can use spiral winding. Lower current, we can go for spiral winding. Now, if the voltage is more than 11 kV, current is small, less than 45 ampere, we go for crossover winding. And if the current is high and voltage is also high, we go for disc winding. Now, among this winding, spiral can be used with circular or rectangular conductor. Helical winding is for large current. So conductor cross section is large. We go for rectangular cross section. Crossover winding, current is small. We go for circular cross. The conductor is circular. And when for this winding, it is again rectangular. So whatever rating I have given for low voltage side, all of you will have this helical type of winding. So conductor area will be current divided by the current density, 3 amp per millimeter square. Now we go for rectangular conductor. Why we go for rectangular conductor? Now actually as the current increases, obviously area of the conductor increases. Now as the area of the conductor increases, then the mechanical strength of the conductor increases also. It becomes difficult. If it is a solid conductor, it becomes difficult to bend and to make the winding. And besides that, we know if it is a large conductor, then there will be, it is a AC device, so there will be skin effect also. That effect also is pronounced. So instead of a single conductor, we go for multiple conductors insulated from one another. Now, when we are going for multiple conductor, we can have circular conductor or rectangular conductor. Now, with circular conductor, the difficulty is that just if we have circular conductors like this, now there is a contact only at the one point, and so the total area divided by the conductor area, that is smaller. That is, there will be much more area space which is wasted. That is one point. Second point is that any circular conductor have a minimum bending radius. So when we have to bend and make the winding, it is difficult with a circular conductor. When we go for rectangular conductor, normally what is used, this is the width, this is the height, and the conductors are arranged. This height is along the height and this is width. So this width to height ratio lies between 2 to 5. So it is more like a copper strip. So it is easier to bend and make the winding, and also it can be arranged in a compact form. So this is a these are 6 parallel conductors arranged. So it is a compact wire. It is much more compact, and space utilization is better, and it is easier to make the winding also. So this is the bare copper on which we will have a insulation. Normally this insulation is paper, double or triple paper, DPC or TPC, double or triple paper covering. And this is the insulation, individual insulation, and this is the outer one. This is the common, this is normally cotton tape. It also acts to arrange the conductor and bind the conductor in space, and also provide the insulation. This is the common insulation. So this individual paper insulation is 0.25, and this outer insulation is 0.5. So if it is a six conductor, then we arranged in this way. This is height wise 3 and width wise 2. It is arranged always in this way because we do not arrange this 3 and 2 in this way, because if we arrange 3 in this way, then the radial depth will increase and it will increase the skin effect. So we want to make height greater than width. So in that case, so height of the if B is the individual conductor height and W is the individual conductor width, then the height of the total will be, in this case, B plus 2 into 0.25, that will be the insulated conductor, into 3 plus 2 into 0.5 on the outer side. Similarly, this will be 2 into W plus 2 into 0.25 plus 2 into 0.5. Now this is for 6 by 2 conductors. You accordingly, the number of conductors you have, that accordingly you can calculate this dimension. Now one thing is that the minimum number of conductors, parallel conductors you should use is 4. Why? Because if you have 2, then you have to arrange like this by this, then this width to height ratio becomes too large. Or if we 3, then also like this, then W by this width to height ratio is too large. So minimal 4 we use. So what now when we go for parallel strips, now we calculate the area of the conductor. If the area of the conductor is lies less than 50 to 60 millimeters square, then we can go for single conductor. If it is more than 50 to 60, then we will have to go for parallel rectangular conductor. So minimum is 4. So what happens if you say your calculated value is 100 millimeters square? Then you will have 4 conductors with 25 millimeters square area. That 50 to 60 is the maximum for individual. It can be less. So for 100, you will have 25 millimeters square, 4 conductors. So once we have the conductor, these conductors are standard size. So whatever be the value you calculate, that conductor is not available. Then we have to go for the, we have to go check with the standard table available. Now I have given, I sent the table. I'll just show it here. This is a rectangular copper strip. Now say you have calculated just 25 millimeters square conductor, I have told that one you can see that 20, this is the W width and this is the height of the conductor. 25 millimeters square, you can see that where it comes. This is 23, 20C. This is the area. This is B, this is W, and correspondingly you will have the area here. So if we have 25, that in the figure table you can see that it is not exactly 25 any, so you have to go for the nearest one. This is 20. Here we have a 25. This is 6.5 and 3.5. No, sorry, 4. 6.5 into the by 4 conductor. Now this is 6.5 by 4. 6.5 by 4. That W to B to W ratio is less than 2. So this we cannot use. So see this one. 7.5 by 3.5. This one, this ratio is more than 2. So we can take this one, we can select this one. So you select this B, your B will be 7.5 and W will be 3.5. So this is the conductor table, is a scan copy I have given. Once you select the conductor, so this dimension is known. Now, once this dimension is known, now how the helical winding is arranged. Now, this HW we have determined initially. Now, this is the yoke. From the yoke and the winding, we should give some gaps for insulation. Now, how much clearance we should give here, I have indicated by HY. That depends on the voltage. Strictly speaking, depend on the high voltage because why high voltage voltage? Because the we want the height of the high voltage and low voltage to be the same. So if you want the low voltage winding height to be same as the high voltage winding height, so this clearance depends on the high voltage voltage.